Good. So the recording has started. So welcome again to today's lecture. So what we will do today is we will start a new topic, and that is on discrete event simulation. So to give you a bit of context, let's look at what we were doing on Tuesday. On Tuesday, we were looking at queues with journal arrival and service times. Now, and so you have seen this depiction quite a few times. So there's one server, there's a queue, and then you have arrivals, but these arrivals are now described by a journal inter-arrival time distribution, and the service time is described by a journal distribution. Now, so on Tuesday, we look at quite a few different types of queues. We look at the MG1 queue, and you have learned about the PK formula. So from the PK formula, you are able to compute what the waiting time is using this formula. And then for the GG1 queue, what we know is you don't have an explicit formula. We don't know what we don't have a formula for the mean waiting time or mean response time. But what we could do is we could get a bound or an approximation. One such bound that I showed you on Tuesday is given here. Now, so that's what you saw on Tuesday. Now, so what you have been doing is you have been trying to learn analytical methods to go and solve queuing problems. Now, so what you are now able to do is you're able to solve a number of queues analytically. And when I talk about solving queues analytically, which means mathematically going to solve it. Now, so what you are given is you're given the inter-arrival time distribution, you're given the service time distribution, and then you go and derive a formula for the mean response time or the mean waiting time. Now, you have actually learned quite a bit over the weeks. You have learned how to solve quite a number of queues, MM1, MMM, MG1, and so on. Now, so you know the part, and so now you know the analytical solutions. Now, and quite often, if you know what the analytical solution is, then that is the most straightforward thing to do. Just plug the parameters into the formula, and then you will be able to get the mean response time or mean waiting time. Now, but I have a piece of bad news for you. The bad news is many of the queuing problems are still analytically intractable. So it's not that you don't know how to solve it. I don't know how to solve it. And in fact, many of the queuing problems that we have today, no one knows how to solve them. So there are still a lot of open problems. Now, if this is the fact, then you may ask this question: what can you do if we have a queuing problem that we cannot solve? So this is what we are going to see what we can do today. Now, so we are going to look at the event of discrete event simulation. So, and the reason why we're looking at discrete event simulation is that there are many queuing problems we cannot solve. We don't know how to solve them analytically. We don't have a formula for that. So what you can always do is you can always resort to doing simulation to go and try to answer the performance analysis questions. So that's why we are looking at discrete event simulation. So when there are no analytical solutions, discrete event simulation will help you. Now, so for today and for the 2 lectures next week, we'll be looking at discrete event simulations. Now, so what we are going to do today is we are going to first understand what are discrete event simulation and then how to structure the discrete event simulation. So this is the first part. And then for next week, we will go and look at a few more topics on discrete event simulation. We're going to see how we can choose the simulation parameters, how to analyze the data, what are the pitfalls that you need to avoid, so how you generate random numbers and reproducibility. So for today's lecture and for those 2 for next week, we'll be looking at this topic that we call discrete event simulation. Now, so in order for us to go and learn how to do discrete event simulation, what we are going to do is we are going to use one motivating example to start with. So in this motivating example, there's one server and there's only one buffer space. So we just keep it simple, one server, one buffer space. There are a number of arrivals now. So we assume that we know when the arrivals will come and how much service time they will need. Okay, so so for this, we are going to assume that there are 9 customers. They are going to arrive at these times. The service times they need are given in this table. Okay, so I'm going to put the table over here, and so we can make use of that later on. Okay, now, so this queue is going to behave in the same way as you have seen before. So if a customer arrives when the buffer is occupied, then the customer will be rejected. If the customer arrives when the server is idle, the customer will get served. If the customer arrives when the server is busy, then you will get into the queue. Now, so given this setting and given the arrival and service times, we want to go and find towards the mean response time. We also want to find the percentage of customers rejected. Now, we will make an assumption that the server is idle at time 0. Okay. Now, so what we will do is we will start with using a graphical solution first. Now, the graphical solution is not going to be a practical solution that you're going to use, but let's start with a graphical solution. And from this graphical solution, we will make a number of observations, and we'll go and see how we can actually go and organize the discrete event simulation. So that's why we start with a graphical solution first. Now, in this graphical solution, we are going to keep track of a number of variables. The first is we're going to keep track of the status of the server. Is it busy or idle? Okay. And then we are also going to keep track of the status of the buffer, whether it's occupied or vacant. Now, so this is just the first part of the graphical solution. So what we have is here, I'm plotting the arrival pattern. So on the horizontal axis, you have time, and when there's a vertical arrow, then that means that's the time at which the customer arrives. So you can see that at times 3, 8, and 9, customers 1, 2, and 3 arrive. And so you can see from here, I'm actually just using this information that I'm given. This is the customer number, and so the sequence number, and then this is the arrival time. So I'm just putting the information of the arrival times and the customer index over here. So customer number 1 arrives at time 3, customer number 2 arrives at time 8. Now, so I'm going to draw quite a lot of this type of graphs, and there's another one on server status. Again, time on the horizontal axis. For the server, is either idle or busy. And then I will keep track of that. Now, and so what I'm going to do now is I'm going to go and work out the graphical solution. Now, so what I will need to do is I will need to go change into the edit mode so that I can show you the change. Okay, just hold on one moment. Now, I think I need to share again. Okay, yeah. So I think you should be able to see 2 PowerPoint windows again. Now, and so what I'm going to do is I'm going to work out the graphical solution. Now, just let me get my pencil going. Yep. I'm going to draw. Yep. Okay. Now, so let's get that going. Now, so what we know is the system is idle in the beginning. So, okay, I forgot. So I've got the arrival pattern here. I'm going to have the server status indicated in this graph. I'm going to have the buffer status indicated in this graph. The buffer can either be occupied or vacant. Okay, and then I will use the departure. So the departure in this graph. Now, so let's start with what we know is at time 0, the server is idle. So what it means is this is the server status until the first customer has arrived. Now, so we are also assume the system is empty. And so at this time, between 0 and 3, the buffer status is vacant, there are no departures. Now, at time 3, a customer arrives. And so what that means is the server will become busy. Now, and how long is the server going to be busy for? We know customer number 1, which arrives at time 1, so time 3, it will need a service time of 4. And so what it means is customer number 1 will finish at time 7. So, and there are no other jobs. So what it means is the server will be busy until time 7, and then the server will become idle again. Now, so I just put down, this is customer number 1. Now, so what we also know is at this time, there are no other jobs coming in, so the buffer should be empty. Now, what we know is that there will be a departure at time 7. So what I'm going to do is I'm going to put time a vertical arrow here to say that there is a departure at time 7. Okay. Now, so what we can see from this graph is the next customer is going to come at time 8. So what it means is from between 7 and 8, what you know is that the server is vacant or idle, and the buffer will continue to be vacant. Okay. Now, at time 8, what you know is customer number 2 will arrive. So what it means is, and also the server is idle. So what it means is the job will go into the server. So at time 8, the server will become busy. Now, how long is the server going to serve customer number 2 for? We can look at the table, and we know that the service time that customer 3 will need is 3. And it comes at time 8, and so what it means is the server will be serving customer 2 until time 11. Okay. That's the one I think I shouldn't be marking it this way. Okay. Now, and so what we know is during this time from 8 to 11, you will be serving customer number 2. And so I put the number 2 here. Okay. Now, and I put a small mark here so that we know that this is the end of serving customer number 2. Now, let's move on. And then now what we know is we have look at okay, now let's move on to the next customer. Okay, so customer number 3, we know it will arrive at time 9. Okay, so and what we know is at time 9, the server is going to be busy. And so what it means is this customer will not go into the server, but you will have to wait in the queue. So what we know is at time 9, the server will become occupied. And which customer will be there? It will be customer number 3. Okay, and so I put a mark here. Now, let's go to the next time here. Okay, and so what we know is at time 11, customer 2 will leave the server because the service will have been completed. So what it means is what we know is at time 11, customer 2 will go away now. So will depart from the server. And so I just put 1 here and 2 here so that I know this is customer number 2. Okay. Now, and what will happen then? What will happen is at time 11, customer number 3 will go into the server. Okay. So now, so customer 3 will go into the server at time 11 now, and it requires 4 units of service. And so what that means is customer 3 will leave the system at time 11. Sorry, it goes into the server at time 11, it will leave at 14. Okay, sorry, 15, because it's 11 plus 4, that's 15. Sorry, the mistake. So this will be serving customer number 3. Okay, but what you know is, because customer number 3 goes into the server at time 11, then the buffer will become idle, will become vacant, and you stay vacant. Okay. Now, so at time 15, what you know is customer number 3 will leave, and so, and there are no jobs waiting in the buffer. So what it means is the server will become idle, and the buffer will stay vacant. And what we have is we have customer number 3 leaving at time 15. Okay. Now, so let's continue. Now, at this point in time, server is idle, buffer is vacant. So what it means is it will be of the same form until the next customer arrives. The next customer will arrive at time 17. So when customer number 4 arrives at time 17, it will go into the server, and the server becomes busy. And if you look at customer number 4, it will require 6 time units for service. And so what it means is customer number 4 will leave at time 23. So what it means is the server will be busy serving customer number 4 at this time. Okay. Now, how about the buffer status? The buffer status will stay the same, because between 17 and 18, after 17, no customers will come until 18. Now at time 18, what will happen? Another customer will come, and so what it means is customer number 5, which arrives at time 18, will go into the buffer. So buffer becomes occupied, and that will be occupied by customer number 5. Okay. Now, so what we know is the server is going to be busy until 23. So what this means is you will, at least until this time, the buffer will be occupied. Now, let's look at this job number 6, which arrives at time 19. What will happen to this job? So what will happen to job number 6, which arrives at time 19? Yep, it will be rejected. So because the server is occupied, also the buffer is occupied, and so this job will be rejected. So I put an arrow here, and this is job number 6. So in the same way, job number 7, which arrives at this time when the buffer is occupied. So job number 7 will also be rejected. Okay. Now, so you have job number 5 here, what you know is job number 4 will finish at time 23, and there's one job in the buffer, and so this job will move from the buffer to the server. Okay, so what I'm going to do is I'm going to put this arrow here to say job number 4 will finish at this time. Oops. And so job number 5 will start to receive surface at time 23, and job number 5 will need 3 units of surface until we leave at time 26. So I'm going to draw a horizontal line here. So the server will be busy serving job number 5 until time 26. Now, what happens to the buffer now? In this job 5 will leave the buffer. So the buffer will become vacant again. And now, but what we know is at time 25, job number 8 will come in. So what you mean, and then job number 5 is in the server. So what you know is at this time, job number 8 will go into the buffer. Okay, and so if you look at the buffer status, then, oops, I'm drawing a bit too big here, because at time 26, job number 5 will finish. Okay, and so what it means is job at time 26, job number 5 will leave the server. So I'm going to put at time 26, job number 5 will, sorry, it's job number, yes, it's job number 5. We'll leave the server, and because 8 is in the buffer, so what it means is job number 8 will move into the server now. And if you look at job number 8, you will need 3 units of surface. It enters the buffer at time 26, so it will go on until time 29. Okay. And what we know is at time 26, the buffer will become vacant again. Now, and so here, it is serving job number 8. Now, if you look at job number 9, it's going to arrive at time 27. So, and job number 8 is in the server. So what it means is the buffer will become occupied again at time 27. And job number 9 will be there. Okay. Now, so at time 29, you know that job number 8 will finish its service. So what that means now is job number 8, my mistake. Job number 8 will leave the server at time 29. So job number 9 will then move from the buffer to the server. And job number 9 is only 2 days surface, and so you leave at time 31. And when 9 leaves the buffer to go into the server, then the buffer becomes vacant again. Now, so job number 9 will get its surface done at time 31. So that, and there's no job in the buffer. So what it means is the server become idle, and the buffer stays vacant. And then what we need to do is you need to put in to here. Now, so this is the graphical model. And so we do have a graphical solution now. We have run through all the jobs. Okay, yep. Let me see, there is a question on the chat. Let me just. Okay, all right, now, all right, yep. And so a student is asking, what will happen if, say, at time 23, you know that a job will depart from the server? Okay, and then what if a job so happen to arrive at that time? Now, you will need to make your decision, so according to your model, what would happen, okay? So whether it's going to have a job departing first or arriving first. So you need to make a decision on that, whether it's sort of the departure will happen first or the arrival will happen first, okay? Quite often, we assume that departure and arrivals won't be happening at the same time because later on we're going to use random number, and events coinciding has a very small probability. But in reality, there may be this situation, and so you need to be consistent and look at your system and say whether the arrival should be occurring first or departure should be occurring first. Okay, so these edge cases, you really need to sort of make a decision based on what's exactly happening in your computer system. Okay, now that's a very good question. Thank you. Now, so what I will do is I will go back to the slide display mode. Now, so we spent a bit of time on coming out with the graphical solution. Now, and I've actually got the sort of very well drawn, so better drawn solution on the next page. And so this is what this is the same as what I was going to do. I have worked out now. So what we have got the graphical solution now. What we wanted to see now is what we can get out of this graphical solution. Okay, now, so the first thing that we can get out of this graphical solution is we can find the response time of each customer. Now, so what you know is this is customer number 1 arriving at time 3, customer number 1 departing at time 7. What you also know is, say, customer number 5 arriving at time 18, departing at time 26. So what it means is the response time of customer number 5 will be 26 minus 18, and so that's 8. And you can do the same thing with all the customers that are not rejected. You can find the response time of each customer. And once you have the response time of each customer, what you can do is add them up and divide by the total numbers of customers served. Then you can find the mean response time. So what it means is once you work this out, you can find the response time of each customer as well as the mean response time. Now, what else can we find? Now, we also came out with a graph with the status of the server. We know when the server is idle, when the server is busy. Now, so what it means is you can actually work out the busy time of the server. And once you have the busy time, you can also compute the server utilization. So that's another thing you can find. Now, this is the departure time, departure of the customers. But here, what we have also indicated is red color. Here means the customer is rejected. The magenta color means the customer is accepted. Now, so these two customers are rejected. And so what it means is from this graphical solution, we can also find the percentage of customers rejected. Okay. Now, the graphical solution is obviously something that you can do using paper and pen, or you can join on a computer screen. Now, but that's not going to be so useful solution for you because there's a lot of manual work. It took us a bit of time to go and draw all those curves there. Now, so what we want to do is we want to learn something from this graphical solution so that we can go and implement a computer-based solution later on. Now, so in the end, what we want to do is we are going to write a computer program that can do this simulation work for us. Now, we will have such a program by the end of this lecture. Now, and what we have learned from the graphical solution is we need to keep track of the status of the server. We need to keep track of the status of the buffer because that will allow us to make the decision. So what decisions we can make? An example is, say the server is busy and the buffer is occupied, then it means the arriving customer will be rejected. And an example is if the server is busy and the buffer is vacant, then it means the arriving customer should go to the buffer. And one last case is, say the server is idle, then what it means is an arriving customer will go to the server directly. Now, so we need to keep track of the status of the server, status of the buffer. What does it mean when it comes to writing a computer program? Then what it means is we will need to have some variables for us to store the status of the server and the status of the buffer. And we should update the values of these variables when the status of the server or the status of buffer have either of them has changed. So that's one thing that we learned. So what it means is we need variables to go and keep track of the server and also the buffer status. Now, from the graphical solution, we can also make a number of observations. Okay. Now, if you look at the server and buffer status, sometimes the server buffer status, most of the time what you see is the server and buffer status do not change. But one thing is we can make an observation to see that at the time when a customer arrives or at the time when the customer departs, the server or buffer status may change at that time. Now, let us see. At time 3, the server status changed, and that's because our customer arrived at that time. Now, how about at time 7? The server status changes because the customer departs at that time. How about we look at this edge? The server status change is because the customer has arrived at that time, and the buffer status change at this time because of a customer arrival. And now, and at this time, the buffer status change, and that's because a customer has departed. So similarly, at time at this time, the buffer status has changed because the customer has departed this time. So what you see here is that at the time when a customer arrives or at the time when a customer departs, the server or buffer status will change. But how about at times, but how about at other times, they do not change? No. So this is a very significant observation. Okay. So we are going to make use of that. Now, so what we are going to do is I'm going to introduce a term called event. An event, and so we call the arrival of a customer or departure of a customer or departure of a customer an event. So an event means a customer arriving or customer departing. Now, so what it means is there is an event at time 3, and that is an arrival event. And there's an event at time 7, there's a departure event. And so there are events at all these vertical arrows are the times at which an event occurs. Now, so this word event is very important because, and you need to know that it means the time at which a customer arrives or time at which a customer departs. So these are the events. Now, just make sure that you recall that the name of this, the title of this lecture today is discrete event simulation. And so now this event is referred to, is the same as that event that we talk about in discrete event simulation. Now, so I'm going to add in another observation now. the observation is that the status of the server and the status of buffer remain the same between two consecutive events. Now, so let's see whether that's correct. There's an event at 3. Now, the next event occurs at time 7. And so these two are two consecutive events, and the buffer status remains busy. So the server status remains busy. The buffer status remains vacant, do not change. How about between event at time 7 and event time 8? No change in server status, no change buffer status. How about the 8 and the next event is time 9? What you see here is the server status remains the same, buffer status remains the same. Now at time 9, that's event, and next event is time 11. And again, you can check between these two events, the server status is the same and buffer status is the same. Now, so you can go back to the graphical solution earlier and check that this statement is correct. Now, what does it mean? Now, what it means is between two consecutive events, buffer status, server status remain the same. Nothing is interesting between two events. Okay. Now, so what it means is we do not have to keep track of anything between two consecutive events. What we need to keep track of is when these events occur. That is the most important thing. Okay. And so what this means now is we have to go and keep track of the timing of the events. Okay. And so we only have to keep track of the timings of the arrivals, the timings of the departure, and that's it. Once we have all these, we can go and reconstruct the, we know the server and buffer status will be the same in between. That is what we need. So events are the important things that we need to know. Okay. Now, so, and events can cause the status transitions. So at the time of the event, the status of the server or the buffer may change. In between events, status remain the same. That is an important observation that we will make use of. Now, so from these two observations from you have seen now, we are going to go to we're making our way towards a computer solution. Now, in our computer solution, what we will do is we will make use of a master clock to keep track of the current time. Now, and what we will do is we will advance the master clock from event to event, because what you know is between two events, status do not change, nothing happens. And so what it means is we only have to advance the master clock from event to event. Now, so what we will do is before we go and do solution on, show you the solution on the code, what we will do is we will go and do what I call an on-paper simulation first. Okay. Okay. Now, so in this simulation, we are going to keep track of a number of variables. Now, I'm going to use the abbreviation MC to stand for master clock. Okay. So MC, the master clock. And for the server, I'm going to keep track of its status, and I'm going to use the number 1 if it's a busy, 0 if it's idle. For the buffer, I use the number 1 means it's occupied, 0 means vacant. Now, so I'm also going to look at the, I'm also going to keep track of the event time. Now, and so the event times will be, as we said earlier, the events are arrivals or departures. Okay. Now, so what I'm going to keep track of is I'm going to keep track of something called the next arrival. So what will be the next customer that will be coming in, and each customer will be characterized by its arrival time and service time. Now, I'm also going to keep track of what the next departure event will be. Now, And so I'm going to keep track of when the customer will be departing, because that will be the, an event. And also, I will also keep track of, for this customer that's departing, what the arrival time will be. Now, I need that because we are going to calculate the response time. Okay. Now, so if we're going to have a customer in the buffer, what we will do is we will also go and keep track of when this customer arrives and how much service time we need, because later on we will need to use that to go and calculate the response time. Okay. Now, so in order to calculate the response time, what I will need to do is I will need to go and accumulate the total response time, and so that's what I'm going to do. And that is the symbol T here, and R is the total number of customers rejected. So that's what we need to do. Now, so we're going to fill in this table. And so in this table, there are a number of columns. So the first column is the master clock, next arrival. I have arrival and arrival time and service time. What's the next departure? And the departure time of that job. And then the arrival time of this departure, server status, buffer status, cumulative response time, and rejection, number of customers rejected. Now, so I will work through this one by one now. So before that, because I will need to edit, and so I need to get out of this mode now. Just make sure that you can still see my two PowerPoint windows. So if that's the case, can you let me know? Because I just want to make sure that you can see what's happening. So are you able to tell me whether you are still able to see two PowerPoint windows on your screen? Yep, good, thank you, you're able to see. All right, now, so we are going to fill this table in. Now, so I've done the first row, but let's see what that means. So master clock, we start on time 0. Now, what we know is the first job that will arrive at time 3, and this service time is 4. Okay. Now, so is there a next departure? Now, at time 0, the customer has not arrived yet. So what it means is there won't be a next departure, and so I just draw a bar here. The server status is 0 because it's idle. No jobs in the buffer, so it's vacant. No response time, no customer rejected yet. Now, what we said earlier is we are going to advance from event to event. And so at time 0, we know that the next arrival will come at time 3, and there's no departure. So next event will be an arrival. So what it means if we will jump the clock from time 0 to time 3, because that will be the next event. Now, and so at the next event, what we know is because this is an arrival, so what it means is a job will go into the server. So server will start to become busy at time 3. Now, so if the job arrives at time 3, it needs a service time of 4. What is its departure time? If you can tell me. It will be 7, correct? Yep. And we also want to keep track of the time that this job will arrive, and so it is at time 3. Okay. Now, we know buffer won't be just one job will arrive, nothing has departed, and so T will be 0, nothing has been rejected. Now, but at time 3, the first customer has arrived, and so we need to see when the next customer will arrive. After time 3, it will be the next customer will arrive at time 8, and requiring a service of 3 time units. Now, so this is the master clock 3. Now, at this time, if you look ahead, the next arrival event is time 8. The next departure event is time 7. Which is the next event? an arrival or departure? So if you know the answer, you can type in the chat. If you look ahead, a departure event at time 7 or an arrival event at time 8, which is the next event that will occur? Is it an arrival or departure? Yep. Now, the way to think about this is arrival will come at time 8, departure will come at time 7. So okay. Sorry, I have to stop for a short time because there is a plane flying over my house. Okay. It was a bit noisy. All right. And so there is a job departing at time 7. There's a job arrival at time 8. Which event will occur earlier? The departure, because it occurs at time 7. 7 is less than 8. So what it means is the next event will be a departure. And so what it means is we go to the next event. We say we jump from event to event. The next event will be at time 7. And it will be a departure. Okay. So, and so if it's a departure, then we see, is there a job buffer? No. And so what it means is the server will become idle and the buffer stays idle and this job will depart. Now, what will be the response time of this job? Because we know the job arrives at time 3 and it departs at time 7. What will be the response time? It will be 4. So we put an answer 4 over here. The job is not rejected. Now, when you and because no job will be going into the server, and so there's no departure, and so we go back to the original status. That I put a bar. That means there's no job, no departure events, and there will be and so the arrival events stays the same. Okay, so that will be what happens now. Okay, now, so I will continue on to the next page. And these are the events that we have. Now, so we will go on and try to fill in this a bit more. Okay, so this is time 7. Okay, and the next, what we look at is what the next events are. There's only one event because the next departure, there's no departure. Next arrival, you will be time 8. So what it means now is we will advance from time 7 to 8. Okay, and what we know is this job will go into the server straight away because the server status is 0 and the buffer. And so what it means is you will go into job straight away now. And so just to fill in the next departure, then what it means is the job arrives at time 8 and it requires 3 time units for service. And so what it means is this job will leave at time 11. Okay, the server status will be 1, buffer status will be 0. So these, because this is a arrival event, these do not change. Now, so again, you need to add into what the next arrival will be. So the next arrival will be at time 9. Okay, and it will require service time of 4. Okay, now, so if we look ahead, there are 2 events, one at time 9 and one is time 11. Which one will occur first? Arrival or departure? So we come to time 9, there are 2 jobs. there are two events, possible events coming next. One's an arrival event at time 9, and the other one is a departure event at time 11. So what will come first? It will be an arrival, because the arrival is at time 9, departure is time 11. So time 9 occurs first, and so master clock will jump to 9. Okay. And now, so the arrival occurs first, and when this job arrives, the surface status will be 1, and the buffer status will be 0. And so what it means is the surface is already occupied. So where will this job go? It will go to the buffer. Yep. So what we will do now is the buffer is going to be occupied. And what I'm going to do is I'm going to put in the arrival time and the surface time of the job in the buffer. So this arrow should actually be pointing here. Okay, so that is the now, so the surface status remain the same. No job has departed, and so this will stay the same too. Now, the next departure will still be at time 11, 8. Now, how about the next arrival? Because this job is now in the buffer, so we look at the table, the next arrival will be at time 17, and the surface time that this job needs will be at, that will be time 6. Okay, all right. Now it's almost 3 to 1. And so what we will do now is we will take a break, and then we will continue on this after the break. So we have a break until 1, and then we will resume again. So if you have questions, you can ask in the chat. So I will also pause the recording for the time being. The recording. So that's where we left off just before the break. We've been filling in these rows. So we will do one more. Okay. So at time 9, what you see is, if you look ahead, there are 2 possible events: an arrival at time 17 and a departure 11. So, and the number 11 is less than 17. So what it means is the next event to occur will be a departure. So we will now advance the clock, master clock, to time 11. Now, so let's see how we deal with this departure. So departure will take place at time 11. And if we look at the surface status, is 1 previously, and the buffer status is occupied. So what it means is when this job departs, the job in the buffer will move into the server. Okay. Now, so let's go and update the response time first. Now, so this job arrives at time 8. It leaves the server at time 11. So what it means is the response time that will be of this job is 3, and so because we are accumulating response time, so I will put 4 plus 3, which is 7. It's not rejection, so we keep 0. Okay. Now, and because the job has moved from the buffer to the server, and so the buffer now is vacant, server continues to be busy. Now, the job that's going into the buffer arrived at time 9, and you will need a service time of 4. Okay, so now the arrival time, the job is 9. Now, what will be the departure time of this job? Can anyone tell me? Or think about when this job starts to receive service. Yeah. So at time 11, this job completes service and leaves. So what it means is this job goes in to start to get surface at time 11. It requires 4 units of surface, and so 11 plus 4 is 15. Yep. And this job hasn't arrived, and so it stays the same. Okay, so we have completed quite a number of rows now. So what we can see from this exercise is that there are a number of things you will need to do. You need to keep track of a number of variables, master clock, next arrival, next departure, status, and so on. Now, so when it comes to implementing the computer program, what it means now is each column is a variable. Okay, and how about what each row means? Each row is an iteration. So this is how you start the iteration. And then from here, if the interface next row, that will be your next iteration of your loop. So this is what you will need. And so this will be how you write your computer program. At each iteration, you will need to update all these variables if necessary, if they change. And then you go from one row to another row. That means you go to the next iteration. And that will be how we are going to organize the discrete event simulation. And that's the reason why we put in some effort to fill in the table. And after you got the mechanics of the table going, you know, this is the logic that you need to do for each iteration. Then you will be able to write the computer program later on. We'll elaborate a bit more. So on the next slide, so let me go back to the slideshow. Okay, I think sharing is still working. So I've done the next slide too, but what I will ask you to do is there's still more jobs coming in and you should continue just to get used of the mechanics. And when you get used to the mechanics, what you can do is you will be able to go and see, how you should be writing a program. Now, we will go and discuss more about the program. Now, so let's look at the logic of the program here. Okay, and so at each step, we advance to the next event that will take place. Okay, so so it is a loop that we have here. So at each time, so earlier what we did was we see there is a next departure event, next arrival event. What is the next event? So we did that earlier, say over here. At this time, the next arrival event is time 9. The next departure event is time 11. And so now this arrival event will occur earlier, and so we advance to the next event. So that's what we have done. So on the top level, the loop, the logic is each time we go and find what the next event is, and then we advance the master clock to the next event. And then now, and so when we know the next event can either be a departure or arrival, then what we need to do is we need to take the appropriate action depending on the type of event. Now, so let's look at how we handle the events. So there are 2 types of events, either arrival or departure. Now, let's go and see how we handle an arrival event. Under arrival event, it depends on what happens. So there are 3 cases that we need to consider. We need to consider whether the surface is idle. If the surface is idle, automatically it means the buffer is vacant, or surface busy, buffer is vacant, or the last case is surface busy, buffer is occupied. So if there's an arrival and the surface is idle, and so what it means now is this customer will get served. So what it means is you need to change the buffer status to busy, but at the same time, because the job has gone into the server, you know when this job will depart. So we need to create a departure event, and the departure event will be the current time plus the surface time of this arrival. So now, and what if the surface is busy and the buffer is vacant? And so what it means now is the job will go into the buffer. And so what it means is you need to change the status of the buffer to occupied. And what you also need to do is to store the time and arrival time and surface time of this arrival in the buffer information. So this is very similar to what we have done here. We store the information in the buffer with it in the variable so that we can make use of that later on. What if the server is busy and the buffer is occupied? Then what you know is the customer will be rejected. So what it means is you will need to increment the counter so that we increase the keep track of that a customer has been rejected. Now, after you have done all this, then what you will need to do is you will need to see whether there will be any more arrivals coming in, and you will need to look up the list of arrivals and then fill in what the next arrival will be. And so this is, and so it means you will look up this table to see whether what the next arrival will be. Now, so this is how you handle an arrival, but how about a departure? Okay, so for the departure, when a job departs, what you need to do is you will need to go and update the cumulative response time. And so what it means is you will take the T that you have been accumulating. Now you need to take the current time minus the arrival time of the departing customer. Why are we taking the current time? We are taking the current time because that is the time that the job is departing, because it's a departure event. So, and so that's the departure time of the job. And if you know the arrival time, this will be the response time. So we are summing up all the response time of the customers. Okay. Now, so after the departure, then it depends on whether the buffer is vacant or occupied. Now, if the buffer is occupied, let's look at this case first. Then what it means is the job in the buffer will move into the server. So then what it means is you need to update the departure event because you know this job will be departing at a later time. So next departure time will be the current time plus the service time of the job in the buffer. And now, because the buffer is now was occupied, but the job has now moved to the server, and so the buffer will now become vacant. Now, what if this departure, after this departure, the buffer is vacant? Then what it means is the server will now be idle, and so it change the status, and the next departure event will be empty. So you will have seen this before. So after this job has departed, server idle, and there's no next departure. So it goes back to Sosaba, and there's nothing for next departure. So you have seen this. So what we are doing is just summarizing what we have done in that table. So the value of the table is you get used to updating these events, and then you can turn it into this type of flow chart so that you can write the program later on. Now, so what's discrete event simulation? And so that is an example of the discrete event simulation, the two the field flow charts that I'm showing you. Now, so what you have seen is you're now able to use that program after you've written it to go and solve a queuing problem with one server and one buffer space. Now, you can obviously make the program more complicated to consider other scenarios. You can consider the case of multiple servers. You can have finite buffer or infinite buffer space. So what we'll now do is we'll generalize it to the case that's one single server and infinite buffer. That's what we're going to do next. Okay. Now, so in this case, the buffer status, we will need to, the buffer status is not just vacant, occupied. So we'll use an integer to go and denote the buffer status. The buffer status can be 0, 1, 2, and 3. 0 means no jobs in the queue. 1 means one job in the queue. 2 means 2 jobs in the queue. So that's the buffer status. Now, and as before, we will also need to store all the arrival times and service time of each job in the buffer so that we can make use of that later on. Now, so if you compare with the single server, single buffer case earlier, what we need to do is if we go from one single buffer to an infinite buffer, what we need to do is we need to go and change how we handle the arrival and departure events. Okay, now, so when it comes to the arrival event, we only have two cases to consider. One is whether the server is idle or the server is busy when the arrival occurs. If the arrival occurs when the server is idle, then what it means is you need to add a departure time, because that job will go into the server, get served straight away, and the server status will continue to be busy. Now, we need to change to busy. Now, so what if an arrival occurs when the server is busy? Then what it means is the job will go into the buffer. And then what you need to do is you need to go and increment the number of customers in the buffer by 1, because now the queue length has grown. And you need to store the information of this event together with the in the queue, so that later on you can make use of that. And that's what you need to do to handle an arrival. Now, to handle a departure, now you need to update the cumulative response time, and that's the same as before. Now, so there are two cases. Once buffer is empty, when the buffer is empty after the job has departed, or the buffer is still not is the buffer is empty at the time of the departure. Now, and so what it means is no job will go into the server, and that's the same as before. Okay, and so there's no change. Now, what if there were jobs in the buffer before the job departed? So what it means is the job will move from the buffer to the server. So, so what it means is you need to update the departure event, next departure time. Now, so this is the same as before. You also need to delete the first customer from the buffer, because that goes into the server. And now the queue length has decreased by 1. So that's what you need to keep track of too. Okay, so this shows you all the flow charts of how you are going to handle all the events. Now, what we have got so far is we have got now you know how to sort of write the discrete event simulation program to simulate a single server queue with infinite buffer, assuming that you have the arrival times and also the service times. Now, so where do arrival times and service come from? Now, there are two possibilities. We want to go and see what you can do with arrival times and service time. Now, sometimes it can be given to you a priori from some sources, and so we will talk about that one later on. Now, you have been learning about all these Markovian queues. Now, let's just see whether we can go and simulate an MM1 queue. Now, if you want to go and simulate MM1 queue, what it means is, and when we talk about MM1 queue, we say the inter-arrival time is exponentially distributed, the service time is exponentially distributed, and so then there's the question is, how can we actually get arrival times and service times if we can generate exponentially distributed random numbers? So this is what we are going to look at now. Our aim is in a short while, what we will do is we will go and simulate an MM1 queue. We will achieve that. Now, so we are going to use Python as an example. So in Python, there are many libraries, and there's one library with the name random. Okay, and so if you want to use the library random, what you need to do is you need to import it in the computer program. Now, so this program, this package random will allow you to generate many different numbers for many probability distributions. So because we want to go and generate exponentially distributed random numbers, then you will use this function random.expovariate that will allow you to generate random numbers that are exponentially distributed. So for a short example here, I first import random, and then I'm going to generate exponentially distributed random numbers with the parameter lambda. So I just use lam here as a lam equals to 2. So now, and so I use this command 3 times. I generate 3 numbers. I got 3 results, 3 numbers, I1, I2, and I3. So these are the numbers I got from Python. So I1 has this value, 0.886 and so on. I2 has this value, I3 has this value. Now, what you see here is each call of the function random called expovariate, it gives me a different number. So, and so these are all random numbers. And so, I mean, if you want to think about an analogy, you think about you toss a die. Each time you get a different number. So these are all random numbers. And so you can think about this library trying to toss a die behind the scene, and then you get these numbers which are exponentially distributed. So that shows you how you can generate random numbers with exponential distribution. Now, so you may ask, are these numbers really exponentially distributed? Now, it's very hard for you to see with just a few values. So what I've given you is I've given you a program together with today's lecture. This is the name of the Python file. Now, the key code here is I specify a certain value of lambda, and I'm going to generate 10,000 numbers using random expovariate. And I store it into an array, into a list X. And what I did then is I computed a histogram of these 10,000 random numbers. So what I'm showing you here is 10,000 random numbers from this function random expovariate, and I plot a histogram. So on the horizontal axis here, I have the value of the number generated. I put them into beans. On the vertical axis, that's the number of random numbers that are actually in this bean. And so that's a very small bean from 0 to a small number. And there are about 1,500 of them in this bean, smaller number in the other beans. This is what the shape looks like for the histogram. Now, and so what you see is there's a high chance for you to get a lower number than a high number. Now, so is it really exponentially distributed? Now, if you want, what I've done is, because I know this is exponentially distributed with a particular, with this parameter lamp. So what I can compute is I can go and compute what's the expected number of random numbers in each bean. And I've drawn this in this red curve here. So what you can see here is the histogram. It's quite close to the expected number of random numbers in each bean. And that is that gives us confidence that the numbers are actually exponentially distributed. Now, so one thing you need to note is the word lambda is actually a Python keyword, so you cannot use it. You shouldn't be using it as a variable name. So that's why I put lam is a lambda. Okay, just a small details. So what you know now is you know how to generate exponentially distributed random numbers. Now, so how do we get the arrival times and surface time? Say I want to generate a system with arrival rate of 2. So I put lam equals to 2 and surface rate of 1. And so I would say put mu equals to 1. So here I will generate the arrival times, so the inter-arrival times. And here I will generate the surface times. So you got the surface times here. But note that the inter-arrival times are exponentially distributed. But how do we get the arrival time? So let's just say you have I1, I2, and I3. Okay. So let's go and look at the time here. So at time 0, the inter-arrival time is I1. And if I put 886 here, so what it means is the first job will arrive at time 0.886. And the surface time is S1 here. Now, I2 is the inter-arrival time. And so from time S1 till the next arrival, the time is given by I2. So if I want the inter-arrival time, so if I want the arrival time of job number 2, I need to take I1 and then add to I2. And that will be the arrival time of the second job. The third job, what will be its arrival time? I will need to take I1 plus I2 and then add the inter-arrival time between these two jobs, which is I3. So at this time, it's actually I1 plus I2 plus I3. So it's important for you to bear in mind when you generate these for arrivals, when you generate these random numbers, they are referring to the inter-arrival time. So if you accumulate them, then you will get the arrival times. Okay. Now, so let's go and simulate an MM1 queue. Now, so what we have done is, I put together what we have learned so far, and then I've written a program called SimMM1 Python, which you will find on the course website. So what we will now do is we will take a look at the program, and then we will run it, and then we will also make some observations. So let me pop up my Python IE. So this is Spider. Just I need to do a new share. Just one moment. Okay. So what you should be able to see now is you should be able to see my Python IDE, the Spider window, and you should also be able to see the PowerPoint slides. Yeah. Let me get myself. Okay. Okay. Now, so this is the same MM1. So that's the Python file. Now, so what we'll do is we'll go through the key points of this file. Now, so we're going to simulate MM1 queue with arrival rate of 1.5 and a surface rate of 3. Now, we need to say how long we simulate for. So I've chosen to simulate 20,000 time units. Now, so we are going to accumulate the number of customers arrived. So the response time, so start from 0 and the number of customers that's been served. Okay. Now, so there are two events, arrival event or departure events. So, so what we will first do is we'll generate the first arrival and the first surface time. So if we go back to here, so this is at time 0, you have the first arrivals, and this what time it arrives and the surface time, and the departure events initially there's nothing. So what I will say is next departure time is infinity. That is something that's convenient for us. Now, and then I will also set the master clock to 0, and the server is not busy in the beginning, and the buffer is empty, and the queue length is 0. Now, so we'll just iterate until the end of the time. Okay, so until master clock, as long as master clock hasn't come to the end time, then what we will do is we will say we continue to iterate. Now, what we need to first do is we need to decide on at this iteration, we need to decide on what is the event that's going to happen at that iteration. And so for that, we will need to see whether the next arrival time is less than the next departure time or otherwise. So if the next departure time is smaller, it means next departure will occur first. And so what it means is the next event will occur at this time, the one that's sooner. And then what it also means, what we are going to say is, we say it's an arrival event. Otherwise, it will be a departure event and it will take place at this time. Now, as we say each time, each iteration will advance the master clock from the event to event. So once you have this next event time, this, I'm going to do the updated master clock, we advance the next event. Now, depending on what the next event is, we are going to have different logic. So if the event is an arrival, we are going to do all this. And if the event is departure, this will be what we are going to do. Now, so let's take a closer look. What if the server is busy? Now, so what if the next event is an arrival? Now, so if we go back to this flow chart, if the event is an arrival, it depends on whether the server is busy, idle or the server is busy. And depending on that, we need to do different things. Now, say if the server is busy, then what we know from here is we need to put the customer in the buffer and then increment the queue length by 1. So if we look at the code, what we have is the buffer content is buffer, and so that's the job that's arriving. So we know what is arrival time, what is departure time, we store in the buffer. And then we increase the queue length by 1. So what this is doing is exactly what is set here. Now, so otherwise, what will happen is, if the server is idle, that means the job will go into the server straight away, and then you will need to add a departure event and change status. So you need to get next departure time is updated as set here, and the server status is now 1. So what you will see is this program is simply turning this flowchart into Python code now. And after that, after you handle all this, you need to go and fill up what is the next arrival time. So here we are going to have the next arrival time, but because we are going to get the numbers by randomly generated, and so that's why this is the inter arrival time, and this is the current time. So then that will be the next arrival time, and that will be the surface time. And because I use the mu here, so that will be an exponentially distributed surface time. Now, so you can go through the code, and then for departure, then you see this flow chart here, and the code here is written in the same way as this flow chart. This is just turning a flow chart into Python. Now, so after we have done all the, and so this is all the simulation. Now, at the end of the simulation, what we have is we have the response time cumulative, and so we add up the response times of all the customers that have departed, and we also keep track of the number of customers that we have served. So to get the mean response time, we just take the cumulative response time divided by the number of customers served, then that will give us the mean response time from the simulation. So what I will do now is I will go and run this simulation, but let me advance the code. Okay. Advance this. Okay. Yep. So what we'll do is I will run the simulation, and I'll make one run, and I've displayed 2 results here. One is the mean response time from the simulation. Is say is 0.60697 and so on. Now, because it's an MM1 queue, we know what the theoretical mean response time is. We can use lambda and mu to go and calculate, and theoretically the response time is 0.666. Now, so what you see here is actually quite close. Now, so I'm going to run it another time, and next time is giving me this number. This simulation one is telling me the mean response time is 0.6704. Now, the theoretical one doesn't change because it doesn't depend on the random numbers. It only depends on the value of lambda over mu. So I run it one more time, and this time you get another value from the simulation of the mean response time. Now, what do we want to learn from this? Now, what you can learn from here is the mean response time from the simulation can be quite close to the theoretical value. So if you go back and look at it, the theoretical value is 0.666, and the first digit is correct, second digit sometimes is correct, sometimes not. So, but it's quite close. And so there's a deviation of less than 0.1. Okay. So, so what you learn from here is the mean response time from simulation can be close, but it's not equal to the theoretical mean response time. Another thing that you learn is each simulation run will give you a different mean response time. Okay, so these are some observations. We will make use of that again later on. But one thing that one thing you need to know is if you do simulation, you are not going to get the exact theoretical mean response time. You can get close to it. Now, so you may ask, how can you get closer? We'll go and have a look so next week how you can get better simulation results. But these are observations that we can see from running this program. Okay, now, so you have seen simulating the MM1Q. Now, so one way of obtaining the arrival times and surface times will be to use random numbers to go and get the inter-arrival times and the surface times. And that's what we did for the MM1Q. Now, and when we started this lecture, we also did some simulation using the graphical method and also the on-paper simulation. But in that, we are using this particular table, and we were actually given a list of arrival times and a list of surface times. Now, can we actually use a given list of arrival times and surface times? Yes, you can. Now, you can do that, and this is what we call the trace-driven simulation. Now, trace-driven simulation can be very useful. Now, think about it. Say you do have a server, and if you are the system admin of the server, what you can do is you can actually make a log of the arrival times and surface times, all the jobs that the server work on. So what it means is, if you have the log from the server, you know the arrival times and surface times. This is what it means is you can have this information. Now, so now then say you have an existing server, you want to change to a new server. And then what you can do is you can use that trace and go and write a simulation program of the new server. And then you can see how well the new server will perform. And that will give you some very useful insight into whether it's making any improvement or not if you upgrade it to a new server. So that is a very useful tool, and that is what we call trace-driven simulation. And so the idea is you put the arrival times and surface time of all your work. It comes in a log. You use that to go and do your simulation. Now, so what I've done is I've given you another program that comes with this lecture, and the name of the file is called same one server trace, and it's over here. Now, and earlier what we did was we used random numbers to go and generate the inter-arrival time and surface time, but now we comes from a trace. And so I'll show you this program. So so we're not using random numbers anymore. And so there's arrival times and surface times, so they are the same as what's in this table. Now, and the rest of the code is almost the same now. So except that when we want to get the arrival times and surface time, we are not getting it from the random library, but we are getting from the list that I've specified here. And so these two lists, arrival time and surface time, have the list of arrival times and surface times, and so I get that from here. Okay. Now, and so the rest of the program is almost the same because the logic is almost the same, except that we are getting the arrival time and surface time from the list. So here's the code that we get the next arrival and surface time. So that we are not doing exponentially distributed random numbers anymore, and we are getting it from the list of arrival times and surface time. So the rest of the program, the logic is exactly the same. Now, one thing I need to note is what I've written here, I assume an infinite buffer. The example earlier assumes that there is one, only the buffer space is one, but then you can modify this program and do the work quite easily. No? So one thing that you will also need to notice, earlier we specify an end time, but now for the trace-driven simulation, what I've done is I'm going to simulate until all the customers have departed, and that's how I stop the simulation. So that is about breaking the loop. Okay. So okay, so you can play with the file, and so that's an example of a trace-driven simulation. Okay. Now, so as a summary, what we have learned today is the bad news is that if for a lot of queues, we do not have an analytical solution. We don't know the formula, how to calculate mean response time, mean service time. Now, if you don't know that, what we can always do is we can always go and do a simulation to go and try to get the response of this type of queue. Now, you have learned that for discrete event simulations, the basic idea is they are events, and your master clock is going to advance from one event to another. And the bulk of the simulation program is to go and handle these events. And what you need to do is you need to go and update the simulation status, the simulation variables, according to what event has occurred. And in our case, what you need to consider will be arrival events and departure events. Now, and to do discrete event simulations, you can have randomly generated arrival times and also surface times, or more correctly, randomly generated inter-arrival numbers, and then you inter-arrival times, and then from there you generate the arrival times. Now, you can also use trace that you have collected from real operations, and in this case, you can do trace-driven simulation. Now, so what I've also shown you is how you can actually generate exponentially distributed random numbers. And I've given you the simulation code for MM1Q and also for the trace-driven simulation. So this is what we have got for today. And that is the first part that we are going to look at simulations. And so in next week, we will continue to learn more about simulations. So if you want to know more, these are a few references they can look up to go and see how you can go and organize and write discrete event simulation programs. So this is so much for today. So if you have questions, you can type into the chat. I also have a short consultation after this lecture. You can also come to a consultation to ask questions. So that's it for today. I will stop the recording. And then if you have questions, you can ask now or come to the consultation. Thank you. Okay, let me stop the recording first, and I will answer the questions on the chat.